this is the trivial. It's plus or minus the trivial minus the sign.
So it's a reflection representation. Right?
Yeah. And so when you restrict it to a long reflection, I mean, you get both of those things. And I don't want, I would prefer to get 0. So you're supposed to change the definitions to get 0 here. Well, let's see if I can do S4 correctly. Well, I mean, this S4 upper delta is the Weyl group of type C2. And the representations are the trivial, the sign, the reflection representation, and the one where the long reflections act by -1, and the one where the short reflections act by -1. These are two other one-dimensional. So 1, 2, 3, 4, 5 representations altogether. And this thing certainly gives you plus or minus the trivial. This thing sorry?
What is it? Is it reflection?
This is the reflection representation of S4, and when you restrict to this subgroup, you get plus or minus this funny one-dimensional. Shoot, look, I actually wrote this down, and it's more likely I'll get it right if I... Anyway, I think that this is supposed to be a funny one-dimensional. This guy, this two-dimensional representation, is supposed to give you the plus or minus the reflection representation. And this guy is supposed to give you the other funny one-dimensional. No. I think this is the one that gives the sign, and then the sign representation. It gives you this other funny one-dimensional.
Funny spelling for other in the other column? One of these two.
Well, these are the two one-dimensionals of the two one-dimensionals of the Weyl group of C2 that are not the trivial in the sign.
Yeah, so that's what I said, they were called other one-dimensional.
Yeah. Yeah, yes.
It's right, funny there. Funny.
Yeah. But thank you. That'd make it clearer. And probably you should change the definition somehow so that this thing becomes sign. I'm not sure about that. At any rate, let me say I think what's well known, so here's a fact about the Weyl group of type BCN, which is S2n upper delta. So this is permutations of 1 up to 2n, and delta is the change of coordinates, this order reversing automorphism. Then
So that is what you did for S4.
that is exactly what I did for S4. Yes, that's right. So I don't remember for sure, but of course this S2n hat is parameterized by partitions of 2n, and this W of BCN hat is parameterized by partitions of 2n into dominoes. I should say that can be divided. You don't have to do the dividing. But in S4, all 4 of these partitions can be broken into dominoes. That's an exercise. But in general, that's not the case. This is an actual condition. And
Condition is equivalent to placing on a chessboard and counting black and white square.
that's a wonderful fact. Yes, that's very nice. And what happens is that I think that everything, I think that every representation of S2n is, every representation tau of S2n is delta fixed. And so it extends, maybe I'll call it tau tilde on this delta S2n, and so up here delta acts, tau tilde E, and so I can write E as, maybe I'll write E of 1, I shouldn't fix the notation in 2 ways, but let's call this tau plus or minus. So E plus or minus can be written as E plus or minus of 1, direct sum E plus or minus of minus 1. These are the delta eigenspaces. And again, if I change the extension, I just interchange these 2 spaces. Each of these is a representation of W upper delta. And I believe that the theorem is that this E, well, for example, E plus of 1 minus E plus of minus 1 is plus or minus, well, it's plus or minus an irreducible of the Weyl group of BCN. In the dominoes case, and it's 0 otherwise. So that's kind of cool. There's a huge amount more to say here.
It's just too confused what you write. Could you repeat what you said in the lower corner?
Sure. So given this representation of the symmetric group, I can extend it to my extended symmetric group of order 2n factorial times 2 in 2 ways. And I'll call those plus or minus. Yeah, the space is E. Sorry. And once I fix such an extension, I get a +1 and a -1 eigenspace for this operator delta. And since delta commutes with WBCN, WBCN acts on each of these spaces. So the difference of those 2 spaces becomes a virtual representation of this group, and it's plus or minus irreducible. Well, it's plus or minus irreducible in this domino case, and it's 0 otherwise.
By the way, the reason you always say plus or minus is because you cannot tell these 2 extensions apart?
That's correct. Though this, in the domino case, this gives a way to prefer one, certainly. You prefer the one which makes the +1 eigenspace bigger.
And did you say that they are always delta 6? Every representation is delta 6?
Yes, that I am fairly certain is true. I mean, this is an automorphism of partitions that's not taking trivial to sign. I don't think there are other candidates. No, actually, I can think of a proof. Anyway, but yeah, this is actually true. It really is. They really are delta fixed. So, well, what would come in the next hour is extending this Weyl group discussion to a Hecke algebra discussion. And this is a really interesting thing to do, but I'm not, well, the things that I've said, you can look up. The Hecke algebra extension, that's the research project.
What's the reference for the stuff you're talking about?
I don't know. Do you know, Mark? For this fact that, well, the fact that the representations of the hyperoctahedral groups, I mean, an aspect of this, what's easy is that, this is Mackey theory, so it says that if you take the Weyl group of type BCN, the irreducible representation correspond to pairs of partitions, pi rho, of partitions of sizes adding up to n. And so what I'm claiming is that this is,
Of course, some deduction from public service activities?
Yes, that's right. And so the claim is that this corresponds to partitions of 2n that can be tiled by dominoes. And the fact that, I've been, well, I don't know. The fact that combinatorially this set of pairs of partitions is in one-to-one correspondence with partitions of 2n that can be tiled by dominoes, this is presumably, I'm sure you can find this in Stanley's enumerative combinatorics. That I'm just sure. I haven't looked, but...
I'm not sure, but you can find it in my paper.
Ah, good. Okay. Okay.
There was a student of Stanley's who wrote a thesis about how the Robbins and Shakespeare paragraphs ensure this is in there somewhere.
Okay.
I don't know the name.
Is it Sheila Sundaram? Is that
Sheila Sundaram, that's certainly a student of Stanley's, so I'll write her name. So these are possible links.
If you want to find incremental, I can show you how to read this projection.
So I'm just trying to think. I suspect that I know, and you can tell me. Let me tell you my guess for what this bijection is, and you can then tell me if it's right or a better way to say it. Sorry?
It's a variant of linguistics.
Exactly. Yeah. So here's here's the story. So you want to start with a partition of 2n and arrange that it has an odd number of parts. The way to arrange this is you throw in some 0 parts if you want. So let me 5, 4, 4, 3. I don't know. 5, 5, 4, 3, 3, 2. How many parts have I got? And I'll add a 0. There's a partition of some large number. And what you do,
You're not sure that it can be tiled by dominoes.
actually I am. This can be tiled by dominoes. But anyway, you write your partition and you put you do C++ numbering next to this, and you add, and you get 11, 10, 8, 6, 5, 3, 0. And in this column now, there are 1, 2, 3 odd numbers, and 1, 2, 3, 4 even numbers. And so this can be tiled by dominoes.
Which condition did you check?
Sorry?
Which condition did you check?
I forget. But
You say so.
This blue column, so this odd number is 2m plus 1, and the blue column has m plus 1 even numbers and m odd numbers. That's the condition.
So it's 4 minus 3 is 1.
4 minus 3 is 1. Yes, that's right. And now you make a Lustig symbol in which you put the even numbers minus, the even numbers divided by 2, and in the first row, and in the second row, you put the odd numbers minus 1 divided by 2. And so in our case, we have 0, 3, 4, and 5, and for the odd numbers, 1, 2, and 5. And now you subtract 0, 1, 2 from each row, and you get 0, 1, 2, 3. You get 2 plus 2 plus 2, and the second 0, 1, 2, 1 plus 1 plus 3. This is, these add up to 6, and these add up to 5, which is 11. These added up to 10, 14, 22. Yeah, so n was 11. So that's... So this is the pair of partitions of sizes adding up to 11. So I started from this partition of 2n. I claim that the condition of being tileable by dominoes is that when I do this, I get this condition on the row sizes, and then, well, you record the even ones and the odd ones. And
So this is not at all what I have in my head, but it might be good, I don't know. But so shall I do it?
Sure. Yes.
The only thing is I need 2 colors.
You're entitled. Jeff won't yell at you.
So you say.
So we got this, to hear me?
Oh, sorry.
5. What was it? 5, 5, 4.
1, 5,
4,
4,
3, 3, 2, 1. 4, 3, 3, 2, 1.
No, no 1.
No one.
There was a 0 in the last row.
Okay. Okay, so this is it. Okay, so I'm looking at the front here now. I'm going to color it in 2 colors, alternating. Oh, no, alternating, sorry. Yeah. Okay, so now I take the red edges. That's one partition. And I take the black edges. That's my other partition. Is it correct?
It's the same.
I think it's easier. I absolutely never understood Lustig symbols.
Absolutely. So, I mean, there's a reason Lustig stuff has other interesting things hidden in it, but that's I can't imagine a better place to end the workshop. That's beautiful.
Thank you.